My goal now is to make a mechanical model that will give me mathematically exactly equal numbers, exactly equivalent results to the electric field in this situation, in particular the electric field at any location E of R. And the way I'm going to do this is to make an equivalent fluid model. And I'll show you how this works. So for this equivalent fluid model, what I'm going to do is I'm going to imagine a very large body of water, maybe something like Cayuga Lake. So over here I'll have the shoreline, right? It's very deep. It's several hundred feet deep. It's 3 miles wide at the widest point. And here I'll denote that it's water, put some waves here on the surface. And the correspondence then between the electric field is going to be the electric field and the flow of this fluid. Now, to get the fluid flowing in exactly the same pattern as I have from a point charge, I'm going to set up the following scenario. So I'm going to imagine I've got a house over here. You know, that's my primitive drawing of a house. There will be some spigot, right? And I'm going to hook up a hose to that spigot, and I'm going to run that hose then along the shore and then down into the very central parts of this lake. And at the end of the hose, I'm going to put a very special device, spherically shaped device, with a series of holes on the side of it that ensure that this device releases liquid outwards equally in all directions. And I'm going to pump a flow of fluid of I, and that's going to be defined as the amount of fluid being pumped down that hose. It'll be measured in mass kilograms per second. And I'm going to pump that liquid right down into the center of this lake. And when I do that, I'm going to need a very special device that's going to release water equally outwards in all directions. So there will be, after things settle down here in the lake, I'm going to establish some kind of a flow pattern, and the flow will be equally outwards in all directions. And as you can imagine, because this is a very large lake, that flow will become less and less as I'm further and further away from my little point source. So the flow out here will be smaller. And this pattern that I establish, my claim is going to end up being exactly the same as the pattern for the electric field, where in this case the correspondence, the precise mathematical correspondence, is that the velocity field set up in the lake is going to match exactly the electric field on a point-by-point basis. And if we can pull this off, it'll be really amazing, because then we won't ever, in principle, have to calculate an electric field ever again. If we can always make an equivalent fluid model for any charge situation, we can simply build the model, let the flow get established, and then measure the velocity of the fluid at any point, and that will tell us exactly numerically the corresponding electric field. Now, for this to work, I need some kind of special device that releases water equally outwards in all directions. Now, you can look in specialized technical catalogs for such devices. If you're wondering if they truly do exist, I was able actually to find one of these on the internet. Let's see here, I've got a figure to show you. This will show you what they look like. Well, there you go. Turns out that, you can buy these practically anywhere. Maybe this particular one isn't as equally outward in all directions as I would like, but you get the idea. You can imagine certainly something like this. Now, getting back to being serious, if we really want to establish this exact mathematical connection, there are going to be certain conditions that this fluid actually has to obey. So there's a little bit of fine print in terms of conditions that our fluid has to obey. But provided it obeys these, this will work out perfectly for us. So here's some of this fine print. There's a particular kind of flow we want to consider. What we need to be considering is the so-called, I'll get all the conditions out and then I'll explain what they mean. But we're looking for a steady state flow of an incompressible inviscid fluid. So here's what these mean. These are sort of technical conditions from fluid mechanics. So in order, what they mean. Steady state means that we're talking about after things settle down. Right? Initially, there won't be any flow at large distances from our little flow ball. Right? It's going to take a while to establish the appropriate steady state flow pattern. But if we wait long enough, the flow will actually settle down to a fixed set of velocities at different distances. And at that point, we'll be able to measure things. Incompressible means more or less what it sounds like. You can't squeeze this fluid. Its density is always constant. That means that the mass density, and we will denote this density by rho, and because it's going to be constant, I'll call it rho sub naught. It's a particular constant value, and that's defined then as the mass per unit volume of the fluid is constant. So what that means is that as this fluid flows, you can't be building up mass in any particular region in the fluid. You just can't squeeze more in there. The mass density is always constant. And the third condition, inviscid, is just a technical term. It refers actually to the fact that there is no friction in the fluid. So it means that this is a fluid that flows without friction, a so-called frictionless fluid. Now, these conditions are not as restrictive as you might think. There are broad classes of fluids that we have everyday experience with that actually obey these conditions, or to a very good level of approximation. Water can be treated as obeying these conditions. The theory of lift on airfoils, to a very good approximation, can be generated this way. You can also, and this is very important for us coming up, current flow in electricity, in electrical circuits, also follows these same types of conditions. And so while we're studying this, this will also be useful for those of you who might be in civil engineering, who might be interested in water flow, or aero engineering, interested in airfoils, and certainly later in this course, some of the mathematics we'll be developing here will be directly relevant and important. So it's important to pay attention to this issue of flow. Now, if we are so fortunate as to have a system that obeys these conditions, such as, for instance, water does to a very good approximation, there are certain mathematical consequences of these conditions. We don't have time really to give you a full course in fluid mechanics, so I will just state these as facts, but they follow directly from these conditions, and these are going to be extremely useful for us. So facts for these flows. The first of them is really the kicker. That is the most important one. If you have these three conditions, it turns out then that the velocity field that you find obeys superposition, just like it does for electric fields. That is really the first key result. This means then if I figure out how to represent point charges or line charges in my fluid, and then I have some compound situation, I can build that compound situation in my tank by making the corresponding mechanical models for the line and sheet of charge, and then the final flow, in fact, will add up just like it's supposed to for the electric field. The second thing is a consequence of the combination of these flow laws and the conservation, let's just move this up a little bit, the conservation of mass if we're talking about a fluid, or charge if we're talking about flow through a circuit. And that conservation law then takes on a very particular form in this case. We measure, notice, flow, and I had mentioned this up above. Flow I is defined to be the mass flowing across any surface per unit time, or in the circuit case, it would be charge flowing per unit time, typically called current in the case of studying electrical circuits. But in any event, that flow obeys the following rule. If I have any kind of a closed surface like so, and I've got some flow pattern going through it, some flow of the fluid, Because it's steady state flow, I can't be building up any mass in here. And because of that, then, I know that whatever current is flowing in, mass per unit time into that region in steady state, has to match the mass per unit time flowing out in steady state as well. And the third and final consequence that will come, and we will actually be able to prove this from the first two circumstances in a moment, is that the point source actually, if you will, works out. That the point source flow pattern V of R will actually match exactly numerically if we set up the right amount of flow pumping down our hose in our situation. That flow, the point source flow, will match the point charge electric field. And that is very critical. Because this means, since I have the principle of superposition as well, since any electric field situation can be composed of summing over the fields from a bunch of tiny point charges, ultimately electrons and nuclei in my system, if I want to make an exact mechanical model for any situation, I simply need to put a fluid point source, like we saw, that sprinkler ball, of the appropriate strengths at exactly all the locations corresponding to the point charges in the electric field situation, and I will then have an exact map because the flows from these point sources will superpose in exactly the same way as the fields from the point charges. So the last thing then we need to prove is this key result, which follows, as I've said, from superposition and the conservation of mass. To understand how this works, we need to understand just a little bit more about the mathematics of flow across the surface, which I've alluded to here in the conservation of mass.